Now we come to the application of friction, which involves basically that how the bodies move under friction and primarily rolling friction. So I'll first discuss rolling friction, then I'll go on to the other applications of friction. Now the rolling friction involves the fact that when a body moves or rolls over one another, then the first body, it actually deforms the second body to some extent. Now this deformation can't be watched with normal eye, but it can be felt when the tires of your car is not fully inflated, or when the cycle that you are riding have tires which are deflated. So what happens eventually is the fact that during kinetic friction you had a force in this direction, and now you have a kind of an incline where the force acts in this direction. So as you can understand very well, that this force F and this force F cos theta are different. They are different, and this is much less. So as the force requirement drops, the rolling friction coefficient drops, and it becomes very easy for the body to move. So if I have a graph showing these three positions of friction, then I have to draw it like this, like this. So this portion is what I call static. This is where the friction is kinetic, and this is where the friction is rolling. So as you can see, the rolling coefficient should be the minimum, all these three. And this is your friction, this is your external force. So mind you, one more thing, that during this position of from O to A, we call friction self-adjusting. So in this region, friction is self-adjusting. Why? Because you see, the body is not moving. You are pushing, the body is not moving. So that implies that your force is balanced by friction force. So that is why when you increase the force, the body is still not moving. So that must be equal to the friction force. So that implies that when you are increasing your force, the friction is also increasing its own force. So that is the point why we call friction self-adjusting during this region. Then it comes to the second aspect of friction. As I can tell you, the second aspect means that how the bodies are moving. So in that case, I will tell you that when the bodies move, say for example, there's an ideal example of a body moving over one another. If I draw this body, and this is say a mass of 10 kg, this is say a mass of 30 kg, and this is frictionless, mirrored surface means frictionless, and this has a friction coefficient, say for example 0.2. So the thing is that if I push, I'm sorry, if I pull the body with a force of say 10 Newton for example, then I have to calculate that what is the minimum force required to move this body. So the minimum force required to move the body, as you can check out from the graph earlier, it is equal to the maximum friction force, and the maximum friction force is mu n, which is mu mg here. So if I substitute the values, I have 0.2 into 10 into 10. So that brings us to 20 Newton. So the force required to move the body is 20. When you are applying 10, that means the body is not moving. So in that case, all these two bodies together will start moving under the action of 10 Newton. But say for example, if I apply a force of 30 Newton, that one happens. I will come to that. What happens when I apply a force of 30 Newton here? So when I apply a force of 30 Newton here, what happens eventually is that this body starts moving immediately. And in that case, if I draw the free body diagram of these two bodies, 30 kg and 10 kg, then 10 kg, for 10 kg, I will have a diagram which will be directed towards 30, this direction in friction backward case. Now this friction will have the reaction for 30 kg. So for the lower body, this is the action force which is pulling the body of 30 kg in front. So this application and this aspect of friction is very important, that when they act between these 2 points, if friction is action force for 10, then it is reaction force for 30. If it is reaction force for 10, then it is action force for 30. It implies that the direction of force drawn on 10 and 30 should be opposite, and according to third law of Newton, they should be equal to. That's for all now. Thank you. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.